complexes, if you analyze, there will be different structures: tetrahedral, octahedral, square planar, okay, different type of structures. But most common will be what? Tetrahedral and octahedral, and some square planar also. These three types. Others are also there, but not very common, not so popular. Most of the time we get this. Now, number of this ligand. Ligand means the species that is getting attached to the central metal cation. That is called ligand. The ligand that is attached to the central metal cation can be in different number depending on the size of the cation. If the size is small, number of such ligand will be also less. And if the size is larger, number of ligands will be more. And that phenomenon is called coordination number. This is called coordination number. So, the number of ligand that is surrounding the central metal cation forming the complex is called the coordination number. For silver gold, coordination number is 2 and the structure is linear. For nickel and copper, coordination number 4. For nickel it is tetrahedral, for copper it is square planar. Both are coordination number 4. Now we have coordination number 6, most common for chromium, cobalt and iron. Okay. Apart from that, you have coordination number 5 also, which is usually rare, but coordination number 5 is also available. For example, FeCO5, iron pentacarbonyl, vanadium pentacarbonyl. So this type of that complex is also found where you have this coordination number 5. So this is regarding coordination number and different type of complex compounds. So this complex compound will vary a lot, and there are a lot of property depends on this structure and all. Now first of all, we need to clarify what is the difference between ligand field and crystal field. Okay, so complex is forming. The basic difference between complex and simple molecule is that simple molecule like NaCl, you have only one type of bonding, that is ionic. If you actually consider the ionic bond is a bond, in true sense it is not a bond, that you know. So sodium chloride, that is only sort of interactive force, attraction. That is Coulombic force of attraction. And what do you call it? This is called ionic bond. Coulombic force or electrostatic force of attraction, and only one type of force is available. Whereas if you take organic molecule or some simple molecule like ammonia, you have only one type of bond. What bond it is? Covalent bond. But this complex compound, you have multiple number of bonds. That's why you call it complex. Because multiple, all sorts of bond, whatever you know, you'll find there. Covalent bond is present, coordinate covalent bond is present, ionic bond is present. All sorts of bond present. That's why it is complex. If you only one type of bond present, that is a simple one. But if there are multiple number of bonds present, then we call it a complex. That's why it is called complex compound. We can call it coordination complexes also, because most of the bonds that we find there are coordinate covalent bonds. That's why it's called coordination complexes. Followed? So these are the type of molecule. Now what is ligand field? When the ligand is approaching to make a molecule, the force field generated is called ligand field. That means before making the bond, initially all the d orbitals of the central metal is degenerate. Degenerate means same energy level. So they are of the same energy level, degenerate molecule. D orbitals. 5 d orbitals are same. But until and unless splitting of d orbital occurs, there cannot be any d-d transition. So this splitting occurs whenever ligand is approaching. So what ligand is doing? Sort of interaction. That is called ligand field. That is ligand field. So ligand is approaching, making the complex, and we are getting ligand field. After the formation of the complex, the separation of energy levels, d orbital levels, that is crystal field. So we are getting two things: ligand field stabilization energy, crystal field stabilization energy. Ligand field before making the complex and crystal field after forming the complex. That is the difference. Before and after. One is before and there is after.
Why ligand always approaching?
Huh?
Why ligand always approaching?
No, because attraction. Ligand is electron-rich species and central metal cation is electron deficient species. So there will be, obviously there is sort of attraction, and because of that attraction it approaches, forming bonds. Always molecule will try to stabilize. So to stabilize, it has to make the bonds to get the minimization of energy, and that's why ligand is approaching so that the compound is formed. Another thing here, remember, for d orbital and f orbital. Okay, so for d block and a block elements, there is electrons. Last electron is there in the d orbital and f orbital. Now, whenever d orbital and f orbital involved, there is a poor screening effect. Poor screening effect will make the residual attraction towards the outermost cell very high because of poor screening, poor shielding. The attraction towards the outermost cell is very high. That's why the field strength is so that it will attract. If there is available molecules or ions that can make a bond, so it will attract. Okay, so that is the reason the extra bond is forming. That is called residual combining capacity. Residual combining capacity. First here it is combined, meets the molecule, and after that also it is attracting other molecules to make a secondary type of bonding. That is called residual combining capacity, and that we find in case of complex compound only. Okay, now let's start with this PowerPoint. Now this CFSE depends on what factor? Already I have told you what is CFSE. CFSE is crystal field stabilization energy. It is the separation of d orbitals after the complex is formed. So the separation of different d orbitals, dxy, dyj, dzx, one set of orbitals, and dx square minus y square and dz square is another set of orbitals. Because one set is there along the plane, another set is there along the axis. Okay, along the plane and along the axis. So they have got some certain difference in nature. Those who are along the plane, their nature, and those who are along the axis, their nature a bit different, obviously, because these dxy, dyj, dzx, they are called primary orbitals, and dx square minus y square and dz square are called derived orbital. That is because it is actually derived by combination of some primary orbitals. So that's why there is a difference. Primary and secondary, that is the difference. dxy, dyj, dzx, they are primary, and they are flanked along the plane. Whereas dx square minus y square, they are called derived orbital. They are combination of other primary orbitals, and finally you get this orbital dx square minus y square and dz square, and they are along the axis. Obviously nature is different, primary and secondary, and not only that, their way of orientation along the in the space is different. Some are along the plane and some are along the axis. When the ligand is approaching, how the ligand will approach? Let's take example, octahedral complex. So in case of octahedral complex, ligand will approach along the axis. So which orbital will be maximum repel? Dx square minus y square and dz square, because there is a head-on approach. The orbitals are along the axis and the ligand is approaching along the axis. So there is a head-on interaction, which is the highest interaction possible. Are you getting me? So that's why the repulsion factor is very high, and there is a energy hiring. And other three, dxy, dyj, dzx, they are along the plane, so the approach is angular like this. So in that case, repulsion factor is less. So these dxy, dyj and dzx are in one level, and other two are in another level, which is higher. So we are getting two sets of orbital. One is called T2g, the bottom one, and EG, the upper one. The bottom one is T2g and the upper one is called EG. T2g and EG sets. So dxy, dyj, dzx, we are getting T2g, and the x square minus y square and dz square is called EG. So two sets of orbital, and in between there is certain gap that is called delta O for octahedral. O for O or OCT, whatever, right? Is short form. So delta O means octahedral splitting energy. Octahedral splitting energy. Similarly, if it is tetrahedral, the approach will be angular. So which one will be more repelled? Those who are along the plane, they will be more repelled. And that's why this T2g will go up and EG will come down. X square minus y square and z square are along the axis, but the approach is angular. So repulsion is less. How the approach is occurring, accordingly the repulsion factor will vary. So octahedral splitting complex energy is higher compared to tetrahedral, because tetrahedral will have 4 ligands and octahedral will have 6 ligands. More the ligands, more interaction, more splitting. Isn't it? Naturally, you have more number of ligands, more interaction, so more splitting. So tetrahedral splitting will be less and octahedral splitting will be more. And there is a relation also. Delta T equal to 4 by 9 delta O. Delta T means tetrahedral splitting energy, CFSE equal to 4 by 9 delta O. That is the relationship between the two. Now this splitting energy depends on certain factors that is in front of you. Metal factor and ligand factor. What are the metal factors? Oxygen state we will be discussing one by one. Higher the oxygen state, more will be the attractive force. Higher the oxygen state, suppose Fe3 plus and Fe2 plus. Fe3 plus has higher oxygen state, so it has got a more attractive force also, and as a result the splitting will be more. So CFSE will be higher for the higher oxygen state. That is the conclusion. Next point, number of d electrons. If you have more d electrons, some of the electrons eventually will go into Eg state. Instead of T2G, it will go into Eg state because T2G is filled. Suppose 7 electrons. So 6 can go into T2G, but what about the 7th electron? It must go into the Eg. It will reduce the stability because it is going the high energy state. So it will reduce the stability of the molecule as a whole. So that's why number of d electron also matters. It will matter. And then the next point, now nature of metal ion. Now nature of metal ion means, what I mean to say, number of atomic number. Higher the atomic number, the metal ion nature will be different, higher and lower if you compare, because in the periodic table, if you go down in the periodic table, so it will become larger size, but as we are going the D block and A block, the bottom one, we have much more number of proton also in the nucleus, so attractive force is also high. So if the attractive force high, you have a poor shielding or poor screening, so interaction with the ligand will be also larger, and that's why the CFSE will vary. At least I can say now that it vary. Whether increase or decrease, that we will discuss. Achha, next is spin pairing energy. Spin pairing energy means if you have more number of electrons, so pairing may be required. First you fill up 1, 1, 1, then maybe more than one is coming, so it will be paired up. Now pairing is endothermic process, so it will absorb certain energy. Pairing will absorb certain energy, and that's why spin pairing energy also will perturb the crystal free stabilization energy. CFSE will be altered by spin pairing energy because it will absorb certain energy. So whatever energy you expect, okay, it will be lesser than that, because if you need pairing energy, it will be absorbed from the system itself. So that's why your energy release will be lesser. So that means pairing also matters. Pairing energy also matters. Next point is ligand factor. These are all metal factor. Then coming to ligand factor. Ligand character. Different type of ligands are there. Some are cationic, very rare. Anionic, very large in number. And neutral also. Different type of ligands possible. Now these ligands all have not same. I give you some idea. Suppose water. Now water H2O, oxygen is electronegative, but it can act as a ligand because oxygen is bearing lone pair. But as a matter of fact, oxygen being electronegative is itself withdrawing electron. It will not be a very good donor, and it can hold the electron density also quite nicely as it is electronegative. So as a donor, capability will be less, not a good ligand. That's why it's a weak ligand. There is a reason behind. If you understand the reason, you don't have to remember things. Achha, chloride ligand. See, it is a large one. So the charge density will be low. Cl minus, there is a single charge, but the chlorine is large size, and the chlorine minus is still larger. Chloride is still larger. So because of large size, the donating capability will be not that good because the delocalized electron. The electron is already delocalized, so it cannot donate very nicely. So it's a poor ligand. Got the idea? Now let's go about some good ligand. Suppose carbon monoxide is a very good ligand. Why? Because carbon bearing some higher electron density. See, what is the structure of carbon monoxide? C double bond O. There is a lone pair on carbon and lone pair on oxygen also. But this lone pair on carbon is actually the donor electron, because carbon is electropositive element. It can donate much more easily compared to oxygen. So carbon part will be donated as a ligand, and carbon cannot hold the electron density very nicely as it is electropositive element. So it will donate very nicely. So it's a good donor. That is number one. Number 2 point. Once it is donated, after that the filled d orbital of the metal and the empty pi star orbital of the ligand, the C double bond, there is a pi star orbital, because C double bond means there is a your sigma and pi bond. So if there is a pi, there is a pi star also. So empty pi star orbital of the carbon monoxide and filled d orbital of the metal, there will be a back bonding. Same thing will occur for CN also. For cyanide, the same thing will occur. So wherever there is a back bonding, there is a partial double bond character, and it will be a very good ligand. So very strong ligand. Ammonia is a good ligand. Why? Because nitrogen is small size, bearing lone pair, and cannot hold the electron density nicely because of smaller size. So it can donate easily. Those who cannot hold properly, they can donate easily. Those who can delocalize the electron, they will not be good donor. So as a result, what is happening? Ammonia is a good ligand. So that is ligand character. Understood the ligand character. Now the more the strong bond formed, the field strength will be higher. So we call it strong field ligand. If the bond formed is very strong, like ammonia donating, giving a very strong bond. If the bond is strong, the field strength is high. So we call it a strong field ligand. But those who cannot make that strong bond, we call them weak field ligand. Like our water molecules, they are weak field ligands. But OH minus is comparatively strong field, because OH minus negative charge is there, so it will be good donor. Okay, comparatively good donor compared to H2O. OH minus will be a stronger bond. Okay, NH2 minus stronger. So this type of ligands will be very strong ligands. So they are called strong field ligand. Last point, number and geometry of the ligand.
But sir, in OH minus, oxygen has the ability to absorb
But OH minus is already negatively charged, so its capacity is filled. Suppose you are hungry, but if you are filled enough, if you are already taken enough food, after that if food is given to you, you will not accept, because already you are filled. So oxygen is also filled. So after that the extra electron is giving. So that is not a problem. But those that when oxygen is hungry, it will not donate. But when oxygen is satisfied, it will donate. So OH minus is satisfied, but H2 is not. Neutral, no? Number and geometry of the ligands. Suppose the geometry, the ligand itself is a very clumsy one, very bulky one. So it has got a different one, character, because in that case, more number of ligands cannot approach each other. And that factor, that is also another factor. That factor is called steric crowding. Just like in organic chemistry we call it steric crowding, same thing is here. If you have more number of ligands and the very clumsy molecular ligand, clumsy one, big one, bulky one, then interaction will be very high, na? In between the ligand system, the interaction will be so high that further ligand cannot approach. So that will strain the geometry also. So number of geometry of the ligand also changes the CFSE. These are the d orbitals. Already you know. Still you have just have a look. So these are d orbitals in the plane, and these are d orbitals on the axis. Those who are on the plane, they will have more interaction if the ligand is approaching angularly. But if the ligand is approaching along the axis, suppose in the x-axis is approaching, see here is the x-axis, if the ligand is approaching along this, so these two lobes are away, approach is in between and nucleus is here, so it can feel some attraction at least. So repulsion will be less comparatively. So what will happen? In this case the dxy will feel less repulsion, but if the ligand is approaching along the x here, the repulsion will be very high, because there is a lobe, some sort of ring means electron density, that electron density is present here, so there will be strong repulsion, because ligand is electron rich, and here the metal, this field d orbitals are also electron rich, so there will be strong repulsion, so they cannot approach. So that's why energetically this and these two will be higher, that is called Eg orbitals, and these three are lower, it is called T2G orbital. Why? G for Garrett. Garrett means even means symmetry. G is Latin word, G first Garrett, that is Latin word. Garrett means even is symmetry. So Eg, they are also symmetric, T2G also symmetric, because d orbitals are symmetric, so they are all symmetric. D orbitals are symmetric as a whole, so that's why wherever d orbital goes, we call them symmetric. So that's why G is there. Achha. Why T T for triplet state, and this is doublet state. Accordingly, call it T2 change.
Crystal field theory explains most of the properties of complex ion bonding. Ligand field theory is actually MO theory applied to complex ions and is only briefly considered in these tutorials. The idea of crystal field theory is that the ligands approach the central atom and create a local crystal-type field, and this affects the d orbitals of the central atom. Transition metal chemistry is dominated by the d electrons that can occupy the 5d orbitals. Here is shown the 5d orbitals of the free central atom. Also the 5d orbitals in the tetrahedral field and the 5d orbitals in an octahedral field. For a free transition metal, in the absence of any crystal field, the 5d orbitals are degenerate, which means that they all have the same energy.
Isotropic means surrounding the ion, the field strength is equal. Any direction, any angle we approach, the field strength is equal. That is called isotropic. All directions equal. That is isotropic. Now tell me, crystal, is it isotropic or not? Crystal lattice, is it isotropic or not? Crystal lattice, any crystal lattice will be isotropic or not? No. Any order structure will be anisotropic in nature. You should know that. Any crystal means it is the order structure, na? Any order structure will be anisotropic in nature. And isotropic means it will be some sort of amorphous behavior. Then only you get isotropic. Like your glass material, it will be isotropic because all direction you get same. But if you take some crystalline material like quartz glass, so in that case it will be anisotropic. So crystals will be all anisotropic. So we are discussing about crystal field. So it will be supposed to be anisotropic. But crystal is not yet formed, mind it. Crystal is forming but not yet formed. That situation I am talking about. In that case it will be isotropic. But once the crystal is formed, it will be anisotropic. Now crystal is not formed. That situation I am telling. Because you see here, all the 5d orbitals are degenerate. That means the complexation has not occurred yet, but going to happen. So that situation is called isotropic. Isotropic, all the orbitals are same energy level. Now after that, the energy will vary.
In an octahedral field, 6 ligands approach, 2 along the plus and minus z-axis, 2 along the plus and minus x-axis, and 2 along the plus and minus y-axis. When a ligand encounters a lobe of the central atom's d orbitals, it raises the energy. Hence, the dz squared and the dx squared minus y squared orbitals, which lie along the x, y, and z axes, are raised in energies, whereas the dxy, dyz, and dxz are out of the way of the ligands and are of lower energy. In a tetrahedral crystal field, 4 ligands approach along opposite corners of the cube, forming a tetrahedral crystal field. In this case, the dxy, the dyz, and the dxz orbitals are raised in energy, whereas the dx squared minus y squared and dz squared orbitals are lowered in energy.
So this is the final situation. These 3 all will
In an
go
octahedral
raised.
crystal field, we say that the d orbitals have an octahedral energy splitting, and we denote this by a capital delta with a subscript oct.
Tetrahedral now. Just opposite situation, tetrahedral.
The tetrahedral splitting of the d orbitals is opposite to that of the octahedral splitting. Also, the tetrahedral crystal field only involves 4 ligands, whereas the octahedral crystal field involves 6 ligands. Hence, the tetrahedral splitting is usually less than the octahedral splitting. For the same type of ligands, the tetrahedral field splitting is equal to 4/9 that of the octahedral splitting. Note that as these splittings increase, if possible, the upper electrons fall down to the lower states. These 2 different electronic configurations are called high and low spin complexes. The reason complex ions display such an array of colors is that the crystal field splittings lie in the visible spectrum. Light passes through a solution of complex ions, which absorbs the light specific to that type of splitting, and electrons jump up. What we see is the light that gets through and is not absorbed.
Okay, let me clarify once more these things. Maybe it is not very clear. So, when the tetrahedral splitting is occurring and octahedral splitting is occurring, the relationship between them that you have seen, that delta T equal to 4 by 9 by delta O. Now, this, what about the color that was discussed in here? I will tell you. So, this, what is high spin and low spin complex? If the splitting energy is high, when it will occur, that the field strength is high. Okay, the field strength is high. That means CFSE, that splitting, the gap between the two levels is high. So in that case, the electrons will try to pair up. Means maximum electron will be filled up at the bottom only. Then only more electron, if sufficiently available, will go into the higher level. Otherwise not. So that is called low spin complex. Because in that case, the total spin are getting paired, so coupled spin are considered negligible, zero. So only decoupled spin, maybe a few, will be remaining. So that is called low spin complex. But if the electrons are going into bottom level and upper level also, why? Because the gap between the two is so low, the gap between the two levels is so low, the T2G and EG level, the difference is so low that it cannot overcome the pairing energy. In that case, electron will not be paired up, rather electrons will be filled up in the T2G level as well as EG level. Suppose you have 5 electrons and totally you have 5 orbitals. So there is two possibilities, either 1, 1, 1 each, otherwise 5, all the 5 in the T2G and non-electron in the EG. Possible? So if the electron is getting filled in the T2G only and not going into EG, then you call it low spin complex, because this is the minimum the spin possible, spin state possible, minimum spin state possible, that is called low spin complex. And another possibility is there, electron is not getting paired up, but it is occupying individual levels. Okay, Hund's rule not applicable, because Hund's rule is applicable for all same energy level. But here we are not talking about same energy level. Some are T2G and some are EG, different energy. So if it is not paired up, then electron will fill in both the T2G as well as EG. Then we call it high spin complex. Now, conclusion is what? If the CFSE is high, electron will be paired up. If the CFSE is high compared to pairing energy, then electron will be paired up. It is called low spin. If the CFSE is lower than the pairing energy, electron will not be paired up and they will be unpaired only. That is called high spin. That's all. Now, one by one we will discuss those points that I was telling with examples and all. Oxidation state, already I told you that ferrous and ferric example. Here we have cobaltous and cobaltic example. So cobaltous, the delta O value is 9200 for the same ligand. Ligand factor we are not considering now. To separately we are discussing. Okay, so only the oxygen state example. Yes. So here cobaltous, same ligand we have taken. That's why, because ligand factor should not come. So same ligand is taken. Cobaltous and cobaltic. See the delta O values 9200 centimeter inverse, and this centimeter inverse is actually wave number, and wave number is directly proportional to energy. E equal to H nu Hc by lambda. 1 by lambda is nu bar. So directly proportional to E, directly proportional to nu bar. So nu bar higher means E higher, energy higher. So here delta O is 9200, here it is 20760. See how much difference. Okay, more than double. Okay, that is difference is what? Only 2 plus and 3 plus. So oxygen state obviously matters. See the gap here and the gap here. It is M2 plus, metal us ion, and this is metal eke ion. For eke ion the gap is quite larger. For us ion the gap is quite less. So that is concludes in what? Oxygen state. Isn't it clear? Oxygen state clear? Okay. Then next is number of d electron. So here we have d7, here you have d8. Here delta, the splitting energy, directly inversely proportional to the number of d electrons. Inversely proportional to the number of d electrons. The more the d electrons, lower will be the CFSE, because it will absorb certain energy. Whenever your extra d electron is coming, maybe it will go into the EG level, or otherwise it will need pairing. Some sort of phenomena will occur, and more d electrons, so obviously will reduce the crystal field stabilization energy. Same molecule, everything same. Only difference is here d electron. Okay, so obviously atomic number must be different. Otherwise, how d electron will be different? Cannot be different. No? Now number of metal ion. Nature, not number. Nature of metal ion. So that is in the periodic table. Cobalt, rhenium, iridium. One below another. Cobalt is the topmost. Below that you have rhenium, and below that you have iridium. See the values. Again the same way. You understand? 2300, 34100, 41200. It is increasing. Why? Because you have pore screening effect. As a result, the interactive force in the outermost cell is higher. So you have a stronger interaction, and you are getting stronger splitting. More the interaction, more the splitting, naturally. So nature of metal ion also matters. With the example is clear. You will get all these things into canvas also. Now spin pairing energy, this single statement only, you have more spin pairing energy, it will reduce the CFS, because pairing energy is the endothermic process. It will absorb the energy. So that's why the CFS is what? Release of energy. And this is exothermic, that means, right? And on the other hand, the pairing energy is endothermic. So it will in the opposite direction. So it will absorb certain energy. So it will reduce the CFS, because both are going in opposite direction.
But sir, the spin energy will be same for the different atoms.
No, there will be slight difference. Slight difference. For pairing energy. Now pairing energy means your plus of spin and minus of spin of electron. So there will be very minute difference actually, not very. I'll tell you one example. From that you will understand what question you have raised. Well, plus substrate and minus substrate, which one is more stable? You see, what do you think? Plus substrate or minus substrate? Which one is more stable?
So both are unstable.
Both? No, I am not telling that. Plus sub and minus sub. Electrons are having plus substrate, minus substrate. Which one is more stable? Plus substrate or minus substrate?
Plus us.
Why? Supposed to be same, no? Because one plus sub, another minus sub, one plus sub, another minus sub. So they are supposed to be same. But there is a very minute difference. There also. Plus sub and minus substrate, there is a very, very minute difference. Okay, there is difference. It's exactly not same. If it could be same, then nuclear magnetic resonance spectroscopy could not be possible. As they are not same, that's why we are taking the help of NMR and doing MRI. Lot of application, right? NMR, do you know? NMR, at least name you have heard. If not, at least MRI you have heard. Medical field, medical application, MRI. It is based on NMR principle. So, and this NMR principle is based on this phenomena that plus substrate is slightly higher than more stable compared to minus substrate. Minus substrate is slightly energetically higher. So here this spin state also not exactly same. That's why I think, it is my assumption exactly, that whatever I feel, that different these molecules, when you take pairing energy, exactly will not be the same. There will be minute variation. Very, very minute though. Always may not be understood. Ligand character next. Ligand character already I told you. You see that why and how the ligand field strength will increase or decrease. So that's I have already tried to give you some idea that which one supposed to be supposed to have higher field strength and which one will have a lower field strength. Could you understand that what I told you? Because of size it may happen, because of your different reason actually. One by one, case to case I can clarify. Like Cl- is large size I told you. So, but it is obviously smaller than I-. I- is larger. So as a donor it is not that good. That's why it is at the beginning. You see in the ascending order you have arranged. in the ascending order. So this is the least in the series. Okay, as a field strength is the least for I minus, then you get Br minus that way. So now Cn minus and Co is the highest, topmost. Why? Because back bonding possible. Partial double bond character is happening, as I already clarified. Are you clear, or should I draw in the board and clarify the phenomena back bond? So first of all, this is the metal ion. The ligand is making a bond, 5 covalent bond. But on the other hand, there is a pi star orbital also. Okay, and there we have pi star. This is the pi star of the ligand, and this is the field d orbital of the metal. There is a back double bond character, partial double bond character. Initially, the ligand is donating at the vacant orbital of the metal. First bonding, that is primary bonding. Got it or not? Ligand has a lone pair. It is donating at the vacant or empty orbital of the ligand metal. That is your primary bonding. After that, field d orbital of the metal and empty pi star orbital of the ligand, whenever it exists, like CO, Cn, they have empty pi star orbital. There is a again overlap. Secondary bond, you can say. That is giving partial double bond character, because already one bond is there and some other bond you are making. So there is a partial double bond character. That makes the bond very, very strong, and that's why metal carbonyls are very stable. Metal carbonyls, iron tetracarbonyl, vanadium pentacarbonyl, okay, and nickel tetracarbonyl, iron pentacarbonyl, vanadium pentacarbonyl. These are all carbonyls, where carbon monoxide is the ligand. They are called carbonyls. Cyanide is also ligand, good ligand, very strong ligand for the same reason. This type of character is there in case of cyanide also. So there is very clearly given, very strong, black colored are very strong, blue colored are strong, the red color medium, and here these are weak.
What about the
Oxalate. Oxalate. You cannot remember, that's why I am not spending much of time. This chart you cannot remember, not required also. I already gave you the clue. How can you decide which one will be strong and weak? That clue you follow. Cannot remember the chart. What clue? What is happening actually? Size matters. Chloride is big size, so it cannot be very good. Electron density will be less, so obviously it will be comparatively poor donor. But strong donor, it will should have localized electron density. Good amount of electron density, localized one, like ammonia. Nitrogen having a lone pair, and that is localized, so it can be a good donor. Ethylene diamine, good donor. So weak field ligand, the splitting will be less, and strong field ligand, the splitting will be high. That's all. Just to make you understand that how it is varying. This is field strength, low field strength, that's why splitting energy is less. But there is a strong field ligand, that's why the splitting energy is high. That's all.
Octahedral splitting. Isolated metal with 5 degenerate d orbitals, that is dxy, dyz, dcx, dx squared minus y squared, and dz squared.
So the situation is like this.
6 ligands approach the
all
d
together
orbitals along the x, y, and z axes from both the sides.
One second. Here, initially, before the field strength is started, it was here. Now, when the ligand approached, they have already reached here. So there is a difference. That is LFSE. Got it? After the splitting will be there, then you get the CFSE. There is difference. Don't mix up the two things. LFSE and CFSE are not the same. Before bonding, here this one isotropic was there. Now it has become anisotropic. Field strength is generated. Ligand approached already. So energetically it has become higher. The gap is LFSE. After that there is a splitting, and in between the T2G and EG there will be a gap. That is CFSE.
as the ligand approach along the axis, as the dx squared minus y squared and dz squared orbitals are spread along the axis, experience more repulsions, acquire more energy. These orbitals are called dGe orbitals. As the dxy, dyz, dzx orbitals are spread in between the axis, experience less repulsions due to interaction with ligands, and hence have less energy. These are T2 orbitals.
Okay, it was that much. Next, Ted Tyler splitting. I think I should end up here. You have the next class, taking the attendance.
But sir, I have a question.
Yeah, sure.
So, how do you define the names of the orbitals like x square, y square, or dz square?
That is the beyond our scope.